Okay, so this is going to be about ions, your cations, anions, and then your oxidation numbers as well. Oxidation numbers have a little bit to do with the way that the electron configuration is, so I'll go into that just a very little bit. What you first need to know is that your two types of ions are going to be your cations and your anions. The way to kind of remember that is look what's bolded. Cations are typically going to be positively charged ions, and that's like the T. The T looks like a plus sign. Or you can also think of it as like a cat. Cats have what? They have positive. There you go. Okay. And anions, the N is capitalized, that's negative. Okay, and we'll give you some examples of that in the next couple pages. Just make sure you have that copied down. All right. So looking at your cations and anions, what you need to know is that metals, which you labeled on your periodic table, are going to mostly be positively charged when they're doing interactions with other atoms. So when they're bonding with other atoms, they're typically going to be the positively charged ions. What they like to do is, if you look at your periodic table, so here's a periodic table here. So if you look at your periodic table, you'll see that the metals, since they are in group 2, they typically tend to have 2 electrons in their outer shell. So this is the group 1 and group 2. These are +1 and +2, which means in interactions, they like to give these electrons up to somebody else. It's easier to give those electrons up to somebody else to complete the outer shell, which I'll show you in a second, versus taking an additional 6 to fill out the outer shell of 8. Or in the case of hydrogen, it's really just 1 in its outer shell. Okay, so I'm going to move this out of the way real quick. Okay, so let's move that. Okay, so like I said, since they are +1, +2 on the metal side, they like to lose their electrons, which means they will end up with a positive charge at the end, because remember that electrons are negative or positive. Are electrons negative or positive? Electrons have a negative charge. So by losing them, we gain positivity. Or we become more positive in nature, right? Okay. The name of the ion stays the same, so lithium atom becomes a lithium ion. Lithium atom becomes a lithium ion. Aluminum atom becomes an aluminum ion. Magnesium becomes a magnesium ion. Okay, so let's see what would happen here. Let's say magnesium, so I'm going to get rid of some of this junk here. You remember to pause this as much as you need, okay? So don't feel like you need to go the same pace I'm going. Let's get rid of this. Sorry about that. So let's say that magnesium we're going to combine with, remember in this rule, as long as we are below group or period 1, which is hydrogen, all these other periods right here, 1, 2, 3, 4, 5, 6, 7, 8, these elements in a row like that, they represent the number of electrons that can be filled in that outer shell. So hydrogen is in group 1, or in period 1, so it really only has 2 positions to put an electron. See, 1, 2. Helium has 2 in its outermost shell. Lithium is in row 2, so it has the capability to hold up to 8 electrons, but it's very unlikely that it's going to have the attractive power in its nucleus to hold on to 8 electrons. So usually it just gives it up to a guy over here. So it's fluorine. All right, so we got this table here. We said earlier that this is +1, +2, +3. This row right here becomes very interesting. The carbon row becomes very, very interesting, because this can be plus or minus 4. And then after this part, it becomes easier to take electrons from somebody else than it is to gain. So noble gases, which is this row right here, they are chemically inert, which means they really don't want to do any bonding. They have a full outer shell, okay? So they don't want to give or take any electrons away. So right there, their oxidation number is 0. But when we get into the fluorine, this entire family right here, this group, these guys are incredibly reactive, just like the group 1 are very reactive, right? And why are they very reactive? These have 7 in their outer shell, 7 electrons. So 1, 2, 3, 4, 5, 6, 7, which means they only need 1 more. So they're really willing to want to take an electron from somebody else, right? So right here, these guys are -1, -2, -3. Okay, So that's where we get the idea of anions and cations from, right? Because in reactions, they're either going to give their electrons or they're going to take them away. So I'm going to go ahead and group this all together. All right, so it's going to be stuck like that. Oh, forgot that there. Don't matter. Okay, so let's get this out the way. None of that stayed. Awesome. All right, so all that's just to say, let's see how we can actually do the electron count here. So when we have a magnesium atom, you know that atoms are neutral, positive, or negative. Which one? Neutral, positive, or negative? Well, we said they're all neutral, so we're going to go ahead and keep it that way, right? So we know that if they have 12 protons, which are positive, it has to have 12 electrons, which means the charge overall, that's going to be negative 12 plus 12, charge of 0. Okay, charge of 0 there. Now, on the other hand, though, if we have a magnesium ion, magnesium is going to want to combine with something that's really, really close to 8. So if magnesium has 2 electrons, because it's in this row right here, there's 2 electrons in its outer shell, 1, 2. That means how many more does it need to make 8? Well, it needs 6, right? So 1, 2, 3, 4, 5, 6. So magnesium is really willing to want to bond with any element in this group right here, because these all have 6 in their outermost shell. So it goes 6 plus 2 is 8. Okay? So in that case, we look at the number of electrons we had here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So magnesium is a plus 2. Or it's going to give up 2 of its electrons. So when we redraw it, it loses one of its orbital shells here. So notice it had 3 shells for electrons, now it went down to 2. It's not really important right now why that is, but just know that there's 2 in the inner, and how many should we have in the outer? We're going to have a full outer shell of 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, because it gave up 2 to somebody else in that other column over there. Okay, so now do we still have the same number of protons, or is it different? Should be the same. 12 protons, 10 electrons, so that's 12 minus 10. That's a charge of positive 2. And that's our charge number, and it's our oxidation number. That's the charge it takes on when it bonds. All right, let's look over here. So what atom is this? If it's got 3 protons, that's the atomic number, right? So we're going to use this to kind of help us. That is, what is that? Let's look at our periodic table. What has 3? This guy right here, lithium, right? Okay, so that's a lithium. I'm going to use the atomic symbol. Okay, and since it's the atom, remember that it is neutral. So 3 minus 3 for the electrons. Notice it's 1, 2, 3 electrons. That's how we draw it. Innermost shell is an s orbital. This is an s orbital, s1, 1s. It's going to have 2. Has a charge of 0, right? Because it's a neutral atom. Come down to an ion, though. So lithium ion. So lithium ion, remember that it's a plus 1, right? So it means it's going to give or take an electron. What do you think? Is it giving up an electron, or is it taking an electron? Well, remember that chart we drew on. This was the plus 1 column, which means it gives up. It adds an electron to somebody else. Okay? So our lithium ion is still going to have 3 protons, but notice I only have 1 shell here, and the most that shell can have is 2, right? Which makes sense. 1, 2, because it lost this guy right here. That's gone. It went to somebody else when it bonded. And what group do you think lithium is going to be very likely to bond with here? Probably these guys over here, right? What are they, halogens? Is that what that is? So that's very reactive columns, right? So you hear like lithium fluoride, lithium chloride, lithium bromide, lithium iodide, lithium acetate. I haven't heard this as much, but lithium is going to really like to bond with these guys over here, because these are 7 electrons. This is 1 electron. When you add them together, they make 8, and 8 is a very nice octet number, right? And let's get this guy back here. The electrons are hanging off, just like me. All right. Okay, let's go down here. Let's try this. Lithium, come on, lithium, stay. Alright, well, don't want to stay. Well, you don't have to stay. Okay, let's try the next page. Okay, so the bottom half of that page says anions. They're on the right side, nonmetals. So you know that staircase there. Those are their nonmetals on the other side. They gain electrons, right? They're going to take away. That's why they're called the -1, -2, -3, whatever. So they have a negative charge or oxidation because they are going to gain electrons. So they have a negative charge or oxidation number because when they bond with things, they gain electrons. Remember that electrons are negatively charged, right? Electrons are negatively charged. Okay? This, when you're talking about nonmetals, you change the name of the atom's ending to an "ide." Okay, so you see here in a second. So oxygen atom becomes an oxide ion. This is just kind of a weird little rule. Doesn't really matter, but you know, just know it. Nitrogen becomes nitride, and iodine becomes iodide ion. Okay, easy stuff. Easy. You can do it. So easy chemistry. Even a child could do it. Okay, so let's look over here. So what atom is this? Well, it's got 17 protons. So that better be. That's a chlorine. Okay, let's look at the periodic table. 17, 13, 14, 15, 16, 17. That's chlorine. Okay, chlorine. Okay, so let's see. Since we're going to do the same thing, since it is the atom version of it, it's 17 minus 17, so we get a charge of 0. It's neutral. Okay, but chlorine, when it becomes an ion, remember the rule, if it's a nonmetal, you change the end of the name to "ide." So this chlorine becomes chloride, right? Like chloride ion. Okay, so that's 17, and remember that what is going to be the rule when we're looking at the periodic table? Is it gaining? Is it taking away? So let's look at it. We said that these were in the -1, right? So that means it's going to take. It's going to take from somebody else. So we had 1, 2, 3, 4, 5, 6, 7. Remember that over here, these guys don't want anything anymore, so this was 0, -1, -2, -3, okay, and so on and so forth. Okay, so it's going to gain an extra electron to fill that outer shell. Okay, so let's go ahead and count up the electrons, keeping in mind that after the innermost shell, which is our s orbital here, after the innermost shell, everything likes to have 8 electrons. Okay, that's the most stable amount of electrons it can have. So let's go ahead and count a regular chlorine atom. So 1, 2, that means it has a stable first shell. Okay, the second shell, 1, 2, 3, 4, 5, 6, 7, 8. So you see there that this was 2, this is 8. So these shells are full, they're satisfied. Let's count the outermost shell. 1, 2, 3, 4, 5, 6, and 7. Just 7. So this outer shell would like to be 8. And so it's going to find other atoms that have just 1 electron in its outer shell to bond with. Okay? So if I added +1 right here, I would be a really happy guy. Okay? Really happy guy. That's the entire idea behind all this stuff. Okay? So let's look at a chloride ion. A chloride ion means that it's gone ahead and done chemistry with somebody else, right? Likely someone from which one of these groups? Let's see. So chloride has 7, which means it's going to look for somebody that just has 1, and which group only has 1 electron in its outermost shell. That's going to be these guys here, okay, or group 1, okay, the alkali metals. Alkali. Okay, so let's look at our chloride. It's probably bonded with one of those. So now innermost, it's going to gain an electron, and it can't gain it here or here. It's going to gain it in that shell that was missing just 1, right? It wants to satisfy that octet rule, that 8 electrons in its outermost shell. Okay, so remember, it's still chlorine, so it still has 17 protons, but now it's gained an extra one in order to fulfill that outer shell. because that's the rule in that group over on the right side of the periodic table. Our charge is going to be a -1, so we have to have more electrons than protons. And we didn't draw any protons in any of this because that's kind of time consuming. But let's go ahead and fill out the shells like we had before. 1, 2. There should be 8 in the second shell. 2, 3, 4, 5, 6, 7, and 8. And remember last time we had 7, so I'm going to go ahead and draw the last in blue. 1, 2, 3, 4, 5, 6, 7. And it gained one more. 8. Okay, it gained one more. So now it has a full 8 in its outer shell. I'm going to go ahead and write the numbers. So I had 2 in this shell, 8 in this shell, and 8 in this one. These all add up to what? 10. 2 plus 8 is 10, plus another 8 is 18 right there, okay? And that's how you do that. Don't worry about this guy. Okay, now let's try one more. So what is this? What is this B right here? This B, 7. So 7 is going to be nitrogen, okay? Nitrogen is 7. It has 7 protons, 7 electrons, has a neutral charge. I already forgot the element, nitrogen there. Okay, but when it becomes an ion, it becomes not nitrogen ion? No. Nitride ion. Okay, so it's still going to have how many in the innermost shell? How many? How many? 2. We're not changing this guy. 1, 2. And before we had, I didn't even count these. It was a very, very bad boy. Let's see, we had, how many do we have up here? So it had 2 in the innermost, meaning that the other 5 had to be in that other outermost shell. So 1, 2, and then we need 5 more to make 7. 1, 2, 3, 4, 5. So 2 and 5, that's boom. Boom, okay? So nitrogen. What is going to be the tendency or behavior? Is it going to give or take electrons? Well, if we look at the table, nitrogen is on the right side, and it's past that happy medium carbon, right, which was the plus and minus 4. So after carbon, after that row of carbon, these are all going to be minuses with the exception of the noble gases, which take and give 0. They don't care. They're already happy. So this is -1, -2, -3. So they want an extra 3 to fill its outer shell. It's really, it's much easier to take 3 away from somebody else than to give up its 1, 2, 3, 4, 5. That's a lot more work to give up 5 electrons to somebody than it is to just take 3 from someone to make that 8 electron in the outer shell rule. Okay, does that make sense? Hopefully the more and more you hear this, the easier the idea becomes. But if not, it's okay. This is more of the job of your chemistry teacher next year to make sure that you understand that. But for right now, just know where we get these oxidation numbers from. Okay, so now remember we needed 3 more because we only have 5 out here. So it would be really happy if it had 8. Remember, we want to try to get to 8. So how many more do we need to get to 8? We're going to take 3 from somebody else. So still this, 7 protons. We're going to go 10 electrons because it took 3. And now we have a -3 charge, right, an oxidation number. So in this outer shell, 1, 2, 3, 4, 5, 6, 7, 8. It took 3 away to make 8. Okay, it took 3 away from somebody else over on the, over in that group, I think 13 it is, so that it could have 8 in its outer shell and be very, very, very happy. Okay. All right. Moving on to this guy. All right, so what do we got here? These are really, really easy. The valence electrons and oxidation numbers are going to go kind of hand in hand. You have your paper here that you can kind of see this a little bit easier than mine. But here is the way that you read oxidation numbers. Okay. Based on the valence electrons, that's the name of it's the oxidation numbers. If you have fewer electrons, you're going to lose the electrons. It makes a positive cation, that's what we just went over on the other page. If you have more valence electrons, you're going to gain electrons. It makes a negative anion, okay? Because more electrons means you become more negative, okay? And if you can read these numbers, which is kind of hard to see, you got +1 and +2 are your oxidation numbers. +1, +2. These are group 1 and 2. And then you have +3, plus and -4. And then all of a sudden we go backwards. We go -3, -2, -1, and then this guy's 0 here. Okay. Okay, make sure you have written the oxidation numbers on your periodic table, so you may want to pause and do that now. Cations have a positive sign, anions have an N or negative. Group 4 can have can lose or gain electrons just depending on the specific atoms that are bonding. Let's go ahead and try this real quick. Bromine. So if you look at your periodic table, oh, and would you have it? There's my periodic table, just appeared out of nowhere. Okay, so bromine, where is it at? Here we are. It's in this last row here before the noble gases. Bromine's right there, so that means it's going to have 7 electrons in its outermost shell, because you can count from 1, 2, 1, 2, skip a few, 3, 4, 5, 6, and 7, where bromine is at. Remember, when we're doing valence electrons, these hardcore transitional metals right here are kind of weird with their valence electrons, because those electrons can slip in and out of different shells easily, because they're kind of more of the traditional metals. So you got 7. Our oxidation number is going to be -1 because it's going to want to take an electron really easy. And since it's a minus, it's going to be an anion. Remember, N for negative, and there's 2 of them, right? Boom, boom, boom. Okay, cesium. Let's look for cesium. You go ahead and try it real quick. Where's cesium at? I found it. Here it is. Cesium, group 1. It's got how many electrons? 1, right? It's got 1 valence electron. So is it easier to gain? Remember, we're trying to get to what number? We're trying to get to 8. Is it easier for the cesium to give up its 1 to somebody else, or to take on 7? It's much easier to give it to someone else, to add it to someone else. So it's going to be a +1. I just wrote the wrong number. +1, right? And that's a cation. Okay, phosphorus. Where's phosphorus at? Find it while I'm doing this, while I'm messing around with this guy. Okay, let's find phosphorus. Phosphorus. Oh, found it. Can you find it before I do? You better. Okay, 1, 2, 3, 4. There's phosphorus. Group 5. So how many valence electrons? It's 5, right? Okay, so is it harder to give up 5 or to gain 3? Because remember, we're trying to always make 8. Okay, it's much easier to take 3 from somebody else. So it's going to take 3, subtract 3 from someone else. Okay, since it's a negative oxidation number, that's an anion. Okay. Ge stands for germanium. Find germanium before I do. See, you have your periodic table handy, right? I found it. Boom, germanium is in this group, right, in the carbon group. So this is plus or minus, right? Because 1, 2, skip a few, 3, and 4. So this is plus or minus, right? So what does that mean for all these other values? Is we have 4 here for valence electrons. Oxidation number could be plus or minus 4. And ion type is cation or anion. Okay. Okay, we got arsenic. Is that right? Is it arsenic? No, it's argon. That's argon. Argon is a noble gas. What did we say about the number of electrons in argon's outer shell? So let's see. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. It looks like it's already content. It's happy with itself. It doesn't need to do any chemistry to find electrons to make 8 in its outer shell. So since this has 8 valence electrons, its oxidation number is 0. It doesn't give up anything. It doesn't take anything. So it is we're going to call this a noble gas. So some of y'all ask why hydrogen is over there if hydrogen only has 2 protons and 2 electrons. It only has 2 protons and 2 electrons. Why is this in the noble gas column? Well, remember we said earlier about how that first orbital, so if I draw a helium with 1 orbital around it, because it only has the one s orbital, right? S orbitals only hold 2 electrons, okay? So since this only has 1 s orbital and it has 2 protons, it means it has 2 electrons. It already has a full outer shell, which means it's pretty chemically inert. It doesn't need to do chemistry with anyone to be content and be happy. So that's why we put it in the noble gas column, because it behaves kind of like a noble gas because its outer shell is already full. Interesting stuff, the more you know. Okay, and last one was boron, right? Boron, you morons. Just kidding. You guys are smartiums. The next person to invent a element should call it smartium for Mr. Bayon's in Ms. Thompson's IPC classes. All right, so boron is in this guy over here. We're in the +3 column. We're in the +3, which means it has 3 valence electrons. Is it easier to give up 3 or to do all the work and gain 5? It's easier to give up those 3, so we're going to say that it's going to give 3, and that makes it a cation. All right. Last but not least, let's go ahead and look at how to do the Lewis dot structures real quick. I'm going to go ahead and skip this stuff over on the left. You can read that yourself. But how do we draw Lewis dot structures? So here is the example for carbon. Let's see. So carbon. Here we go. Carbon is in group 14. But remember, we're doing valence electrons, so we skip all this guy right here. 1, 2, 3, 4 valence electrons. And the way that valence electrons work, they work by the Hund's rule and Aufbau principle, which you don't need to know for this class. But basically, you draw the symbol. So carbon is C. And since it has 4 electrons, you start right here and just start dotting like that clockwise. Or counterclockwise, rather. You can go 1, 2, 3, 4. Okay? Really doesn't matter, but by convention, we're going to go ahead and say counterclockwise, as long as you don't go 1, 2, 3, 4. You can't do that, okay? You can't bunch them up. Each direction, up, right, left, and down, so from here to here, each direction can only have up to 2 electrons total, but you got to do them one at a time. You got to fill them up one at a time. So since it had 4 valence electrons, we went 1, 2, 3, 4. Let's try it for some of these other ones. Okay, hydrogen, really easy, right? Just has how many electrons in its outer shell? Well, it's group 1. All the group 1 elements have 1 in their outer shell. So that's really easy to do. So let's go ahead and do that real quick. Remember, we're going to start here and just go 1 valence electron. Dunzaruni, okay? Let's see, P is for phosphorus. Where's phosphorus at? 1, 2, 3, 4, 5. So it's got 5 total. 5 total. Let's go ahead and dot these bad boys. 1, 2, right? Wrong. 2, 3, 4, 5. Just like that. Just like that. Okay, Ca is for calcium. Not California, but calcium. There's californium on here, though. Think so, right? There's californium. See if you can find californium real quick. Californium. It is way beyond this periodic table. It's like 252, but it's CF for californium. Anyways, calcium is in group 2, 1, 2 valence electrons. So we got, let's go ahead and boom. Ready? 1, starting here, 2. Good. AR, we're not going to make that mistake again, is argon, right? Noble guess. So that means it has how many? All these guys are going to have full outer shells. So with the exception of helium, that means it's going to have 8. Helium's got 2, right? Okay. So we got 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. Easy stuff, right? Go ahead and pause it and try for the last 2, chlorine and aluminum. Go ahead. I'll wait. Pause it. Try it. Try it. Try it. Try it. Stop copying me. Just try it. Find it. Okay. All right. So chlorine is 7 in its outer. Aluminum has 3, right? So we're going to go 1, 2, 3, 4, 5, 6, 7. Did you dot it like that? Good. Aluminum 3, 1, 2, and 3. Okay, so that's how this stuff works. Know that you really have to understand how the ions work, and using the periodic table to do the ions really matters. It's a building block for getting the oxidation numbers and also getting the electron configuration of the Lewis dot structure. Okay, this is something that is really going to set you up to understand chemistry next year really well. I hope that helped. Bye-bye.